So Chapter 5 is going to focus on working with trig equations and identities. So we're going to be seeing these six trig functions a lot. And we're going to be using a lot of the information from Chapter 4. There was those reciprocal identities, those Pythagorean identities, and we're going to bring in some other identities in order to be successful in this chapter. So the first thing we want to do is remind ourselves that we can use identities to make some problems easier. So problems like you see in example 1, A and B. A lot of the times when you'd see problems like this, using the given values to evaluate the remaining trig functions, and I give you a trig function, you would draw a triangle and then you would use Pythagorean theorem to find the missing side and then list your six trig functions. You can still do that, and it's like I said, some problems might be easier to do that than others, but I want to show you and kind of process with you the use of identities. So in this problem here, we have the cosecant of pi over 2 minus theta equals 3. Remember, one of the identities, the cofunction identities, says that this right here means that the secant of theta is equal to 3. Okay, so if we know the secant and we know the sine, we can use those two to figure out what cosecant is equal to and what cosine is equal to. So we know that sine is 2 times the square root of 2 over 3. Then cosecant has to be sine flipped. So that's going to be 3 over 2 times the square root of 2. But we can't have the square root of 2 in the denominator, so we multiply the top and bottom by the square root of 2 over 2. So you have 3 times the square root of 2 over the square root of 2 times the square root of 2. This part right here gives you 2. Multiplied by that 2 gives us a 4 in the denominator. Right? Then we were given what secant is equal to. Secant is 3. So that means cosine has to be 1 over secant, or 1 over 3. Okay, so then that would be 3. Now for tangent and cotangent, we have options. We could find the cotangent first, or we could find the tangent first and just use the reciprocal identities then. I want to use smaller numbers as possible, and I don't want to deal with radicals in the denominator. So I'm actually going to use the tangent definition of sine over cosine. So we have the square root of, we have 2 square root of 2 over 3 over 1/3. Well, we know instead of dividing by 1/3, we can multiply by the reciprocal. So if we're going to then do 2 square root of 2 over 3 times 3 over 1, well, the 3's will cancel, and we're left with 2 times the square root of 2. Now the cotangent is going to be 1 over tangent. Well, again, we can't have the square root of 2 in the top and bottom. Or sorry, we can't have the square root of 2 in the bottom, so we're going to multiply the top and bottom by the square root of 2. So then we get the square root of 2 over 4. All right, so we were able to find the 6 trig functions, and that didn't take too much time. Is it faster than drawing a right triangle? Maybe, depending on how good you can use the Pythagorean theorem. This one, however, we only know one function. We know the cotangent. Yeah, we can use cotangent to get tangent, but then to get the other ones, we would have to use an identity, and then that can get a little bit complicated. So this one, it might be better to draw the triangle. Here's our theta. cotangent is tangent flip, so instead of opposite over adjacent, it is the adjacent over the opposite side. And then we can do 6 squared plus 5 squared equals c squared. Well, the left side, 6 squared plus 5 squared, that's going to be 61. So 61 equals c squared. So then c is equal to the square root of 61. So because we have a radical, yes, some of our functions are going to have to be rationalized. So then we can do sine. Sine is the opposite, 6 over the square root of 61. Well, we can't have that, so we'll multiply top and bottom by the square root of 61. Oops, over 61. And then, like we've done before, for the cosecant, instead of flipping our simplified version, I'm going to flip my original one back here. That way we don't have to rationalize anything. Then the cosine is the adjacent over the hypotenuse, and again, we can't have that. So it's going to be 5 square root of 61 over 61. And then the secant is going to be cosine flipped. And then tangent, well, we already know what cotangent is. Cotangent was 5 over 6, so that means tangent is 6 over 5. Now what we have to do is look at this other piece of information. Cosine is less than 0, so cosine's negative. So that means cosine in secant must be negative, but sine must also be negative because cotangent is positive. Well, if cotangent is positive, the only way for that to be true is if we are in quadrants 1 or 3, and because cosine's already negative, that means we are in quadrant 2 or 3, so then these have to be negative as well. So the triangle probably was a bit quicker in that one than using identities for that same problem. So we can use either one. So now down here we're going to talk about some statements that we're going to be using a lot. And the problem is, if you just look at them at the surface, you think that they're all the same. But there really are some minute differences. Like an equality is a statement that's always true. 2 equals 2. 3 plus 4 is 7. 6 squared is 36. Those are things that are always true no matter what. So an equation is something that is true sometimes or conditionally depending on the value of the variable. So like 2x plus 3 equals 11. That statement is only true if x is equal to 4. So we solve that equation to get what x is to make that statement true. And then an identity is a statement that is always true for all values of the variable within its domain. So you might say, well, how is that different than equalities if it's always true? Well, the equality doesn't have x or any variable. You see no x's in these examples up here. But down here in the identities, we see x's. And you see that they're on both sides. 2x plus 3x equals 5. That is an identity. That is true for any value of x that's in its domain. Now, if you look at the last example with fractions, we say, oh, x can't equal 1 or negative 1. But other than that, x can equal any number, and it's true. So this is what an identity is. In section 5.2, we're going to be proving identities. So what we're going to do in 5.1 is to build our skills to enable us to prove identities. So example 2 says use the fundamental identities to simplify the expression. So we want to make the expression a single trig function or a value if we can. And then we have some tips for simplifying. Combine or break apart fractions, use reciprocal identities. So we're going to focus on those skills today. Tomorrow we'll focus on other skills, but today we're going to be combining or breaking apart fractions or using reciprocal identities. So right here we have the secant of x minus tangent of x times sine of x. And it doesn't equal anything, so we're not trying to solve. So our answer is not going to be x equals something. What we're trying to do is simplify this. Instead of having 3 trig functions written out with 2 separate terms, we want to see, can we combine that a little neater. So we know that the secant is 1 over cosine x minus tangent is sine over cosine, times sine of x. Now you might say, well, how did I know to convert cosine or secant into 1 over cosine and tangent into sine over cosine? If we can't combine anything, one of the most basic strategies is to change everything to sine or cosines if you're stuck. Well, we didn't really have much to do here. We couldn't factor anything. We couldn't combine like terms. So I decided to switch to sine and cosines. Now, what we can do is say 1 over cosine of x minus sine squared x over cosine x. Okay, so now that they have the same denominator, we can combine those. 1 minus sine squared x over cosine x. Now on our identity sheet, we can see that 1 minus sine squared of x is equal to cosine squared of x. So cosine squared of x over cosine x. Now because this is cosine squared of x over cosine squared, we can actually cancel the numerator, one of the cosines in the numerator, with the cosine in the denominator. And that will just give us cosine of x as our answer. So one of the things that can be confusing is realizing that this right here is really cosine x times cosine x. And if we have that over cosine of x, well then you can easily see that why those cancel off. So just keep that in mind. Now, letter B, we have sine squared of x equals cosecant squared x minus 1. So again, if we want to simplify that, we want to look at our identity sheet and see what we can do. Anytime we have a trig function squared, we should think about using the Pythagorean identity or one of the offshoots of it. So again, on our sheet, this equals cotangent squared. Now you might say, well, why didn't I change sine into something with cosine in it? The reason why I didn't do that is because that would give us another 1 to deal with. By changing cosecant squared x minus 1 into, it should be cotangent x. By converting it into cotangent x, that gets rid of that minus 1, which can make things more difficult if we have that there still. So now we know that cotangent is really cosine over sine. So cotangent x is cosine squared over sine squared. And then the sine squares will cancel, and we are left with the cosine square. We're left with cosine squared x. All right, now letter C gets a little bit difficult because we have tangent squared y over secant y plus 1, and then we have a plus 1 outside of that fraction. So the first thing we're going to do is see if we can work with the first fraction, because this one hanging out here, that doesn't affect anything in the fraction. On our identity sheet, tangent squared is equal to secant squared minus 1. So then secant squared y minus 1 over secant y plus 1 plus 1. Now again, how did I know I wanted to switch tangent squared to secant squared? Because in order to simplify things, we need to have the same trig function. And we don't have a way to convert this denominator into tangent of anything. So we had to go the other route and convert tangent into secant. Just like here, um, we wanted to convert things to maybe combine our sine, and by changing cotangent to cosine squared over sine squared, now I can combine that with the sine squared that was already there. Now sine squared y minus 1 is actually a difference of squares. Remember, the difference of squares is this formula right here. So we can rewrite this now as secant square, not secant squared, secant y minus 1 times secant y plus 1 over secant y plus 1, and that that plus 1 on the outside. Well, the secant plus 1's from the numerator and denominator will cancel with each other. So then we're left with secant y minus 1 plus 1. The minus 1 and plus 1 will combine, so we're left with this. We are left with just the secant of y. All right, now letter D, we have cosine squared over 1 minus sine x plus cosine squared over 1 plus sine x. We can't combine those fractions because those are different denominators. And one of the strategies we have for adding fractions is to get common denominators by multiplying the top and bottom by the denominator of the other fraction. So I multiply the first fraction by 1 plus sine of x, and I multiply the second fraction by 1 minus sine x. So what that will do is that it will allow me to combine these two fractions. So I have cosine squared x times 1 plus sine x plus the second fraction, cosine squared x times 1 minus sine x, all over the common denominator, 1 plus sine x times 1 minus sine x. The numerator, I can factor out a cosine squared from both of these terms. This has a cosine squared. This has a cosine squared. So we have cosine squared of x, and then in parentheses 1 plus sine x plus 1 minus sine x, all over the numerator changes into 1 minus sine squared because of what we talked about here. It's just going in reverse. A plus b times a minus b, we have 1 plus sine times 1 minus sine gives me 1 minus sine squared. And yes, you could FOIL that out if you want to and simplify it, but that is something that we should be comfortable with doing and simplifying a little bit quicker. All right, so now we have cosine squared x, and I can combine like terms in the parentheses, 1 plus sine plus 1 minus sine. Well, plus sine minus sine go away, so we have 2. And 1 minus sine squared is equal to cosine squared. And then these two can cancel, and we are left with 2. So these problems can be difficult just because there's a lot of things that you should be looking for. And there's really no right or wrong way to do it. There's just an efficient way and then the least efficient ways. So these do take practice of looking at doing, what to look out for. Here, I saw that we had two fractions that did not have common denominators, so I knew, all right, we have to combine them at some point, so let's go ahead and do that. Now, this one is probably a bit easier because we don't have two fractions, we have just two trig functions here. So we can simplify this again by switching them to sine and cosines. Tangent is sine squared over cosine squared. And then secant we know is 1 over cosine. And then we can rewrite this as multiplying by the reciprocal. And then that's going to give us a situation where our cosines can cancel off. So then we are left with sine squared of x. So it didn't get much simpler, but it did reduce down to, instead of two trig functions, down to one. Now this one, we have 1 over cotangent squared plus 1. On our identity sheet, this right here is equal to cosecant squared. And we know that cosecant is just 1 over sine. So if we flip this, this becomes sine squared of x. And now it is as simple as it can go. Now, it didn't get much simpler. You may argue, well, we only have a couple things at the beginning, and then when we convert cotangent squared x plus 1 to 1 over cosecant, that's still pretty simplified, but we can go a little bit further to make, instead of a 1 and a cosecant squared, we can change that just to sine squared. So this lesson is actually a little bit more confusing than 5.2 because you just are told to simplify without any specific goal. Again, we're simplifying as far as we can go until we either have one trig function or a number like we had right here in this example. We just got 2. So thanks for watching. Make sure to like the video and subscribe.